Well, we were talking about the def operation. So I think of the def operation as being like a definable power set operation. So def x here will be the so I'm going to call this the definable power set of the set X. So where's the full power set here? This consists of all of the subsets of X. Right? Just to write out the obvious. Def X, these will be these Y's that are subsets of X, but which I've got a definition for. For Y over the structure X with epsilon. So what we're trying to do is formalize this idea, express this set theoretically. Right? So just at the very end of last time, I gave this interpretation operation here. So I'm talking about the bottom of page 47 here. So this is one of these Y's. It's a collection of W in X right, such that evaluation H makes the formula coded by U over the structure X about this W come out true. So I can write that like this. So this is, recall this notation here. This is the valuation that assigns objects in X here to, I could say here H is in QX. It assigns objects to free variables in X. And at the V0, zeroth space, we allow it to vary over the objects W. So it picks out those W's that this formula makes true about its other variables, which are assigned parameters by H here in X. So again, just to remind us, typically U, this is a code of some phi, right, V0 up to VK here. And so H, so H of U, H of 0, this will be W here. So what we're looking at are the collection of W's such that the formula phi, and now we've got W here, H of 1, H of 2, up to H of K. So we're looking at the collection of W's in X that make this formula come out true. Right here, for this H in QX. I don't know whether there are any questions about that before I go on, because we're going to build on this now. So this is what I'm calling, so this is the interpretation of over the structure X using the valuation H, the formula coded by U here. So this is one of these gadgets. And definition 317 just says def x is the collection of all of these. So let me write it out in. So it's a collection of these interpretations. H in Qx and U a formula. So here's the formula, characteristic function of formulae or codes of formulae here. Okay, so now, I mean, the observation is that, of course, over the full power set, there's no restriction on subsets. I mean, this can be enormous, and we have no control or no handle really on what this power set looks like. This is much more controlled, right? We're saying I'm only going to take the subsets of X here where I've got a definition for them, right, in some parameters. So I'm not going to have any more new subsets than I've got definitions. Later, we'll be counting how many definitions we have. Well, in brief, we've got countably many formulae here. And then the other way to change the definition is to change these parameters. Well, there are only as many parameters here as there are objects in X. So this gives, the def X will be a very controlled subset, collection of subsets of X. And in fact, there are only many def X will only have the same size as X, at least if X is infinite, right? So it's not going to add many more things to X. Right? So we'll explore this def X function. So let's look at lemma 319. First of all, it says X is in def X. And if X is transitive, then X is contained in def X. So, okay. Now, any finite subset, sorry, of X. Yes, the size of, this is omega. Any finite subset Z of X here will be in def X. And lastly, here, again, there's emphasis on the use of choice here. If X is infinite, then this is the remark I just made, the size of def X is actually just the size of X. So let's see how this goes. I mean, this is just a template for other things to come. If you want to show something is definable, you've got to provide a definition. Right? So I need a formula that I can use to get the set that I'm after into def X. Well, what I want is a formula here so that actually it picks out everything. After all, we want the whole set X to be definable. So I want a formula that will pick out the subset of X, which actually is all of X. Well, then the answer is easy, because I could just use the atomic formula V0 equals V0. That's true of everything. So I do that. What is X then here? It's the collection of W in X such that the formula V0 equals V0, again, this has just got the one free variable V0 in there, and I'll take as valuation the H function, which just returns W for 0 here. And as W varies over X, any W makes this true, of course, so it gets plopped into the set we're defining here. So this is everything that's in X. Right? So here is an interpretation. So I then defined X from that. So this is one of the things that's in def X. So I'm going to leave 2 and 3 for exercises for you. So this will get you acquainted with this def function here. So please think about how this works. I mean, this is central to the construction for Gödel's model L of constructible sets here. So this def will be coming back quite a lot. Okay, 4. Assume X is infinite. I want to count how big def X is. So firstly, recall what Qx is. This is a set of valuations into X. So I'll write it out once more. It's those functions, domain omega into X, so that there's some natural number such that for all later numbers, it's the same. So essentially, a function here in Qx, there's a finite initial segment where everything is interesting, up to Hn. And then there's this final segment where everything is just repeating this value all the time. So there are as many objects in here as there are these interesting initial segments, because the tail doesn't really count. So the cardinality of Qx is just that of the finite functions into X. And if X is infinite, this is just the size of X. So the latter here as X is not finite. The collection of all finite sequences from an infinite set has the same size as the infinite set. Okay, so that deals with how many valuations there are into the structure X. Which is one component of the specifications for def X. And then the other component is, as I said, the number of formulae that we can use the valuations upon. And the language is countable, so the number of formulae is countable. So we just say that next. So if I just look at here, this is just the collection of codes of formulae. This is countable. So I'm just going to say then the cardinality of def of x here. This is just going to be less than or equal to the cardinality of f plus the cardinality of qx here. Well, this is omega, or LF0, and here we just said this was the size of x here. X is infinite, so this is just the size of x. Okay, so 2 and 3 exercise. Okay, so that's telling us how long, how large this def x is going to be, right? So we have some further exercises down here. There's a variation on def. And this is def sub 0. So this comes from exercise 3.6. Def sub 0 of x, right? Let's see if I can just think of this in another way. This is a collection of interpretations over x using formula u here, and interpretations functions h, where, okay, u is a formula. But there's actually only one free variable there inside u. So the free variables of u is just v0. Now I could say here then the h in qx as before. But actually, the free variable here is just v0. And this is the thing that we're going to alternate, right? So I could write that as saying, right, it's a collection of those z's. This is the whole def x here. Such that z is the collection of things in x such that x epsilon thinks, well, let's suppose u is the code of phi here. And we have w, where, again, the free variables of now phi is just w. Sorry, it's just v0. So as it were, the rest of h here isn't playing any role because there are no more free variables in phi to assign objects to anyway. Yeah. And we're letting w vary over x. So it's the collection of objects, right, which are, when I run the definition, I only pick up one object Z here. And I realize I haven't quite, this is incorrect. Right? I tried to extemporize on that and I got it wrong. This is the correct thing to say here. I look at the things which, I look at what, what objects make phi true over X. And actually there's only one object, Z. So we call it a singleton, Z. And so I look at the collection of singleton Z that are definable by just one free variable formulae right here. So there's only one thing in here. So it uniquely picks out some object. So Z is somehow singleton definable over here. So such a Z we can just say is outright definable. The formula doesn't need any parameters, just immediately picks up this Z. So it's outright definable. Here. And definition 320 calls this OD star. Right? So such a Z here. So definition 320. You may look at this a bit further, but it's not an essential part of our development here. Is OD star outright definable? If for some beta, Z is definable in this sense, right, over V beta. Sorry, so OD star, that's related to this here. So to be outright definable, you have to be a singleton definable over a V beta. So it's interesting to see which class of Zs this idea picks up. Well, any ordinal is OD star. Maybe I'll come back to this, right, later. Okay, so you can ignore this little bit here for now. Okay, you might like to think about how you would demonstrate this, right, over some V beta or other. Okay, in the next section, I want to omit everything other than the correctness theorem, which I just want to mention, 321. So in section 3.5, accept the correctness theorem, which is 321. which I have to say something about. Though we aren't going to give a proof there. So what we've got, right, what the correctness theorem does is relate the two kinds of, well, two kinds of truth, I could say, but two kinds of meaning that we've established. From the very outset, we talked about a formula being true in an interpretation. So I said we might have a class term W, and I think about the idea of phi being true interpreted in W, where we had that superscript W. And the idea there was we just took the quantifiers of the formula and we just restricted them to W. So exists X's became exists X in W. That's how we interpret the form in W. So I can then ask, again, looking from outside with my formula, I can say, well, does the formula become true in W using interpretation? Right? So that's one way we kind of can think about meaning, attaching meanings to formula by interpreting it over a domain W. Now, of course, we're doing something rather similar here when we talk about our codes of formulae being satisfied by evaluation in a structure X. And it's an obvious question to ask how these two ideas relate. One, we're standing outside and talking about interpretation. And the other one, we're kind of going into set theory and looking at set structures X and sets which code formulae U, and then these valuations. And we've given a mathematical definition for how a valuation makes a code of its formula true in a structure X. And we need to kind of do a bit of cleaning up, right? Because we want to just check that we've not got any conflicts going on. We want these two ideas to deliver the same kind of results. In other words, we want our definitions to be correct. And that's why this is called the correctness theorem here. So let's just look at it and see what it's actually saying. So I've got a formula of L phi here. And it's got three variables. V vector, so, and these are the variables Vj0 up to Vjm. Then we can prove in ZF that for any structure X and for any M, well, this is an M plus 1 tuple. Just try and stick with it. For any Y vector, which is an M plus 1 tuple from X here. Well, this formula, its code number of this formula, with the Y vector evaluating the free variables, I better have that J0 is 0. Right? Because when I do def, I always assume the formula has the very first variable V0 as one of its free variables. Oh, sorry, no, I take that back. We're not talking about def here. I don't need this restriction. We're only talking about satisfaction. We're not talking about def here. Sorry, rewind. So the valuation makes the formula true here. I want this to occur if and only if, when I look at the formula phi and I substitute the y's in for the v's, I want this formula to be true when I relativize it to the structure X. And that's what I was trying to say. We were relating these two kinds of meaning. Here we have the formalized definition, which we've given within set theory about this set structure and this valuation sequence, this set, which is a function. And standing outside, when I look, I take my formula and interpret it in the structure X. So formally, if we were to give a proof of this, which we're not, we would do this by induction on the complexity of the construction of the formula phi. We'd assume it's true for the components, the subformulae of phi, and then prove that it was true for phi itself. But this would be quite wearisome and wouldn't be terribly instructive here. So I'm just going to ask you to buy this, the correctness of the correctness theorem, and we're just going to assume that this is what we have. And we're going to use this equivalence later on in later sections. And again, like the reflection theorem, it's something that we kind of prove in ZF one theorem at a time. We couldn't prove this. I couldn't put a for all phi down in here and get this to be true, because that would be tantamount to being able to talk about truth, and it would contradict Tarski's theorem on the undefinability of truth. So I have to say for all phi out here, not down in here. But anyway, that's a technical point. So unless there are any questions about that, I will march further on. I'll say a little bit about section 351. So as I said, we can ignore the rest of let's see. Right, I do want to say a bit from on page 50 on page about 351. So you can ignore everything except the correctness theorem and what I'm going to say here for about 351. So we say theory is consistent. So this is just some discussion here. Theory T such as ZF. Saying it's consistent means that I can't prove a contradiction from the theory. So for any sentence sigma, we cannot prove both. So we cannot have T proves sigma and T proves not sigma. Or equivalently, you could say T cannot prove naught equals 1. Because if you've got a falsehood, you can prove anything from a falsehood. So if I could prove naught equals 1, I could prove sigma and not sigma for any sigma whatsoever. So we can abbreviate this as Conti. So this is what we're going to use later on when we're going to think about theories being consistent. I'm just emphasizing the point that when we think about a theory being consistent, we mean it can't prove a sentence and its negation here. And I'm going to use these two things equivalently. We can't have both a proof of a sentence sigma and its negation, or we can't prove naught equals 1. So both of these, I'm just going to abbreviate this situation, saying that this, we can't prove naught equals 1, or we can't prove a sentence with its negation. I'll abbreviate both of these, or either of these, as Conti. So that's what I want to take here from 351. And again, I've more or less talked in the past about, when a theory is consistent or not. But 351 just talks about this in a little bit more detail. So the rest of the discussion in 351 we don't really need. It's just this bit here. So from 3.5, I want, just to recap, I want you to take the correctness theorem, or at least the idea of the correctness theorem, and at least what it does, right, or know what I'm referring to, and I talk about it again in the future. And I want you to take away just this idea of consistency down here, Conti. That's what we need from there. I'm sorry, I need a little bit more. I'd forgotten the section continues over the page. I want to do 326 as well. Sorry, I'm being slightly disorganized here. Actually, at the moment, I'll skip 326. I may come back to it later, but I'll let you know if we do. It might be more appropriate at a later stage. So let me outline then what we're going to do in the constructable hierarchy, which is chapter 4. So it's called the constructable hierarchy. Sorry, my writing has gone to pot. Constructable hierarchy. So I want to contrast the construction that Gödel gave with that of V. And I said this before, but so the V hierarchy here, we start out with V0 as the empty set, and at successive stages, we take the whole power set of the previous level. So the next slice of the cake up here is, can be enormously bigger than V alpha. Right? It's the whole collection of all possible subsets. And at limits, we take unions. and V is the union of the whole lot. Now, the L hierarchy that Gödel defined is potentially a thinner universe that sits inside V. It contains all the ordinals here. It starts out from the empty set, but now it just takes the definable power set. Right? This is the difference, this clause, and the others are the same. So now lambda is the union of the previous ones. And L is the whole lot. That's what we're going to do. So essentially, this is definition 4.1. Okay. And at the moment, this is said without prejudice as the relationship between what L and V is. Right? So typically, one might draw V. Right? But L could be a proper subclass of V. So here would be V, and here would be L, and here would be ordinals going up the middle. Now, it may or may not be that V equals L. We'll discuss this later. That actually, by this process of definable power set operation, we do end up picking up everything in the power set. It's possible. And we'll see a situation where that happens. Right? But we'll also see that, well, I'll also be stating the fact that we can't prove in the axioms of ZFC that V equals L. So it may be that L is a proper subclass of V, or it may be that L is all of V. So there's that kind of ambiguity is yet to come. Right? But we're going to investigate properties of these L alphas that come here in this definition. Well, the first thing to note is that def was a absolutely definite function. It was given, we said earlier, it was given by a definite term. So the relationship between L alpha and L alpha plus 1 is something that's absolute for transitive ZF minus models. And this is lemma 4.2. The term L alpha is definite. Or if you like to put it, the function that goes from alpha to L alpha. And hence is absolute for transitive ZF minus models W. And it's just because the def function is absolute. The def function we saw was given by a definite term. And the L alpha hierarchy here, this is given by a recursion involving definite processes. Here at successive stages, we just apply this definite function, and taking a big union of the previous stages is a definite operation. So the map that goes from beta to L beta is definite. It's defined by a definite recursion. And so is absolutely definite. So again, to think about it, if I've just got some W here, here are the ordinals of W, here's some beta in W, right? If W thinks that Y is L of beta, here, so it's got some set in here that it thinks is L of beta. This happens if and only if Y really is L of beta. And this is terribly important, right? For the discussion that comes. Right? So again, this is W, this is one of these transitive models in which all of ZF minus is true here. Okay, so next time we'll continue looking at the properties. We'll be proving things about the properties of the L hierarchy. And we'll be doing that for the next few lectures.